Hello. Today I'll be speaking about open source video processing pipelines. This is a huge topic, way too much to cover in this short 15-minute video. If you go to the QR code, there's a wiki with a lot more information. Here we have the most interesting open source video processing pipeline that I know of. These are the frame glasses, the circuitry, the Verilog, everything is open source. Of course, all except for maybe the most important piece, which is the manufacturing system. So they have a camera, they have an FPGA. Here you can see the video pipeline. In the upper left-hand corner is the camera. It feeds into a camera pipeline on the FPGA. It gets sent over SPI to a microcontroller. It goes off to the cloud where some AI recognizes the image, sends the data over Bluetooth back down to the microcontroller, goes back into the display pipeline, and gets displayed in a little display on the lens of the glasses. Let's take a closer look at the frame camera pipeline. So an image comes into the camera. It gets over MIPI. It gets input into the FPGA. It gets converted into from bytes into pixels. It gets debayered. From there, it gets cropped, JPEG compressed, encoded, and stored into the large RAM. And from there, it's sent off to over SPI to the Bluetooth. Sort of very typical camera pipeline. Here's one that I'm working on. It's for drone videos, camera sent over MIPI, they're compressed, encrypted, IQ encoded, transmitted over radio, and then IQ decoded, decrypted, decompressed, and sent over display. So while the previous one was completely open source, this is a more typical situation where parts are open source and parts are closed source. So for example, MIPI is a very common standard, but it's actually a closed source. You have to pay money to even read the spec, and you have to pay some licensing fee. Even if you don't pay it directly, one of your suppliers will be paying it. Same thing on the output display side. We're all familiar with HDMI. It turns out that's a proprietary spec. You also have to pay money to a licensing fee to use it. It's built on top of the older open source DVI protocol. And so you have to be careful when you're building a product to be using open source DVI and not closed source HDMI. And of course, the lawyers make it intentionally very vague as to where the boundary between the two is. So a big part of drones is the radio communication. Here we have completely open source RunCam Wi-Fi Link version 2. It takes a DVI out of a camera and transmits it over, basically over Wi-Fi. But in order to minimize the latency, there's no error checking. It just sends the data and assumes it's correct. You use it broadcast mode. So the case, the circuit board, the software is completely open source. You can do what you want with it. If you're doing more complex radio communications, then maybe you're doing frequency hopping to avoid jamming in military situations, then there's a Blade RF, uses a Xilinx FPGA. Okay, so let's take a closer look at the pieces of these video pipelines. It starts off with a camera. On the left is what we used to think of as a camera. Nowadays, most people think of a camera as what you get on a cell phone. Pretty amazing what they do with multiple lenses, multiple focal distances, multiple exposures, even sometimes time of flight sensors. But the engineers think of cameras more like something like the Raspberry Pi camera. You get, 12 megapixels for like $50. And then you can plug them into a Raspberry Pi Zero, $10 or $15. It's got a port for the camera. It's got a DVI port for displaying. It's got a USB 2. It's got a GPU that does compression. You can also do a parallel RGB out. Just amazing how much functionality you get for how little money. You may have studied basic lenses in high school or college, and of course if you look at the patents for the iPhone lenses, they're now way more complex, and it's the typical for every single part of the video processing pipelines. There were some simple solutions, and the various pieces, everybody keeps optimizing their piece, all the pieces keep getting much more complex. And of course there are tons of pieces to choose from. So just for image sensors, there are 874 image sensors in this one online database. And in my research, I found that there are additional image sensors which aren't even listed in that database. What do we do with all of this stuff? Well, often people build camera stacks. So here's the ArduCam USB shield. On the top, there's a lens, there's an image sensor. The bottom board is a USB 2 or USB 3 device, and then in between them they have an adapter. So there's so many image sensor communication protocols that they need a whole bunch of different adapter boards to be able to connect the different ones to a USB 2 or USB 3 baseboard. This is partially closed source. What's more interesting is the Recamera camera stack. This is completely open source. And it's this beautiful metal case. It has to be metal because the middle board in this case is a microcontroller, often a RISC-V. That generates a lot of heat, so it needs a metal case to conduct the heat away. But still, looks really nice. Again, completely open source. What do we do with these camera stacks? Well, the first thing you might want to do is defective pixel correction. So if you have a short in your image sensor, then that'll show up as white dots on a black background. You want to correct that by averaging with adjacent pixels. If you have an open circuit in your image sensor, then that'll show up as black pixels on a white background. You may want to do pixel binning. So what happens is, for $50 you get a 12 megapixel camera, but my display is only 1.4 megapixels. So what makes sense is to average in adjacent signals. You get better noise immunity, and you shrink down the number of pixels, so that simplifies life. So that'll so typically pixel binning will reduce your image size by a factor of 4. Historically, what people did a lot of Bayer filters. So what they would do is the gray substrate in the upper right-hand corner would be the substrate, and then they'd put red, green, and blue filters on top of that so that only those colors would get through. And of course, they do use twice as many greens as the other ones because the human eye is more sensitive to green, so they want that to be more accurate. And then they get a number of point datas for each of the points, but the human wants to see RGB, so you want to see a red, a green, and a blue colors all on the same pixel, and so they do debayering to convert that into RGB. Very well described on Wikipedia if you want to learn more. That, of course, increases the size of the data by a factor of 3. You may want to do video cropping to the image. On a desktop, it's pretty easy because you can just end up with a different size video. On a real-time processing system, often you have a certain display size. You want the video to cover the whole display. So if you're doing like a digital zoom, you may have to do some stretching as well. A bit more complex, not that difficult. We also need to be aware of camera spectral responses for red, green, and blue. The camera has a certain spectral response, the display has a spectral response, the eye has a spectral response, and of course they're all different. So if you take a look at this woman's face on the left, she looks like a zombie or something like that, and that's because the spectral responses are different. So what they do is they rotate the colors so it looks more like the face on the right. We're very sensitive to the color of human faces for good evolutionary reasons. Of course, we care a bit less about the colors of the greens. And then often the final step is to display it. There are a huge number of display interfaces of various levels of complexity. Often we choose DVI, HDMI, but you really want to get it on your computer, so there are these DVI to USB 3 dongles. So less than $10, really good solution. So then you can display it on your computer, maybe to an online meeting, record it. And the way that these work is they have a double frame buffer inside. So the HDMI or DVI signal comes in, it gets written to one frame buffer. In the meantime, the USB is reading from the other frame buffer. At the end of the image frame, they swap buffers and the process continues. Of course, that takes a lot of memory, and on a microcontroller, you don't have a lot of memory. So what do you do if you want to do video on a microcontroller? My recommendation is to use libmpix. What it does, it has a ring buffer. And so the pixel comes in, gets written on one end of the ring buffer, it gets read out of the other end of the ring buffer, and in between they can do processing on that ring buffer. And what's particularly interesting is they're introducing single instruction multiple data, basically vector parallelism. And so at that point you'll be able to do even a lot more computations on the image as it streams through the microcontroller. Really, really smart idea. I like these guys. But what if you want to do something even more complex? Here we have fisheye dewarping in real time. You really need a chip called an FPGA. FPGAs, simple story, they're great for video processing. And ideally, you'd like to use the open source FPGAs. By open source, we don't mean that that the chip itself is open source. They're all proprietary, but they're supported by open source tool chains, typically YOSYS and NextPRN for synthesis of the circuitry. I'm really happy with these open source tool chains. There's a lot of eyeballs looking at it. They get to be really fast. They run really fast, very bug free, very nice to use them. They run on my Mac too. Very happy with them. If you're using this, there's a rapid, and it's also evolving rapidly. There's a rapidly increasing number of FPGAs which are supported by these. The ones that are interesting are, perhaps most interesting, are the Lattice chips, because they have a 2.5 gigabit per second MIPI interface. So the Lattice 17 and 40 have this interface, so recommended. There's also Lattice 33, which is closed source, and then you have to use the vendor supplied tools. What I really like is the European Olimex GateMate. It has a 5 gigabit per second SerDes interface, so some interesting things one can do with this. And of course, the simplest thing is you can just connect up the Waveshare OV5640 using lots of parallel RGB. $16 for the fisheye lens. No focus is required at runtime. The rectilinear lenses do require autofocus, and so they're more expensive, running at $26. Here's a zoomed in view. In January, you should see the $79 iSpy Zero coming out. It's got the Raspberry Pi form factor, so you can just plug a Raspberry Pi Zero into it, kind of click them into place, and then you can use Raspberry Pi parallel imaging out. At 90 Hertz, you should be able to do 1.5 pixel image using the Raspberry Pi Zero as a MIPI bridge. Looking at applications, farming is a big issue. There's actually open source ecology has a whole collection of open source tools, equipment for farms and for other applications. But what they need is something for measuring photosynthesis. So, for example, in Poland, they have the government flies over fields and it measures the photosynthesis. Because that's a very good measure of the health of the plants, and then the amount that the farmers are paid are determined by that. And so currently what happens is people typically use the DJI multispectral cameras. It's got RGB and infrared in the top row, and the bottom row is for navigating. And here you can see the nominal frequencies of the DJI cameras on top of the photosynthesis spectral response, and you can see it doesn't quite align. It's not really the best tool for measuring this. What you'd really like is be an open source photosynthesis spectrum cameras, so where the frequencies measured by the cameras map into the peaks and valleys of the photosynthesis spectrum. Okay, so what's the overall recommendations? This is a very complex field. If you find a shrink wrap solution that does what you need, just use it. That's by far the easiest solution. If you're doing low bandwidth applications, my recommendation is use libmpix on Zephyr OS. Typically, if you want to use MIPI an open source FPGA, use Lattice NX with MIPI CSI and DSI. That'll give you 2.5 gigabits. If you want 5 gigabits per second, then you should really use the European-made FPGA gate-made. And for the other FPGAs, you can use Raspberry Pi MIPI CSI to DVP. That'll give you 1.5 gigabits per second. There's a whole issue of what to do with longer range cables. You can read a whole bunch about that on the wiki. Originally, this was written as a conference article for the open source OSHOP Open Source Hardware Conference in Chemnitz, Germany, but they limited it to 10 pages. It may go into a book article, and there's just too much content. So I created a wiki, wiki.pythonlinks.info. You can search for what you're interested in. People really like it. Venkat said there's a lot of work condensed in the wiki, good work. Joshua said it looks nice, organized a bit like a series of chests in a gold mine. Simon said, Christopher Lozinski, I've been reading through the Python Links site. It's fascinating. So lots of really good content there. Here is the QR code to reach the wiki.pythonlinks.info. Contact me on Mastodon, send me an email, lozinski@pythonlinks.info. If you have any questions, you're probably not the only one with those questions. Thank you very much.